There is a Waymo Robotaxi operating right now in San Francisco that has never once looked out a window. It has no eyes. It has no human instincts. And yet it completed over 4 million driverless miles by the end of 2025 without a single fatality. Meanwhile, a licensed human driver causes a fatal accident somewhere in the United States every 25 minutes. The machine is not better at driving because it thinks faster. It is better because it perceives the world in ways that human biology simply cannot. What is actually happening inside that car, the sensors, the data, the millisecond decisions, is almost nothing like what most people imagine. The reason this matters right now is not abstract. The National Highway Traffic Safety Administration reported 40,990 traffic deaths in the United States in 2023. That number has barely moved in a decade despite seatbelts, airbags, and lane-keeping systems. The bottleneck is human perception. We miss things, we get tired, we misjudge distances in rain and darkness. Autonomous vehicle technology exists today that statistically outperforms human drivers in controlled conditions. The gap between that capability and widespread deployment is not primarily technical anymore. It is regulatory, economic, and deeply political. Tesla's full self-driving subscription crossed 2 million active users in early 2026. Waymo is expanding into Atlanta and Miami. Zoox, owned by Amazon, is testing closed-loop robotaxis in Las Vegas. If the regulatory path clears in the next 3 years, the insurance industry alone faces a restructuring worth hundreds of billions of dollars. Your car insurance premium is priced today on the assumption that you are the driver. That assumption is cracking. The story of autonomous perception starts in the 1980s, when researchers at Carnegie Mellon University built a modified van called NavLab, a rolling computer lab stuffed with cameras and processors the size of refrigerators. It could follow a road at 20 miles per hour in good weather. That was the ceiling for 2 decades. The fundamental problem was not computation. It was data. A camera captures light and turns it into pixels. But a pixel has no depth. You cannot tell from a photograph alone whether an object is 3 feet away or 30. Human eyes solve this through stereoscopic vision, 2 eyes separated by about 65 millimeters, with the brain calculating depth from the slight difference between what each eye sees. Early autonomous systems tried to replicate this with stereo cameras, and it worked, but only close up. Beyond about 30 meters, the baseline was too small. The depth information degraded. Engineers needed something fundamentally different, something that did not rely on light the way a camera does, but could measure distance directly, the way a bat measures a cave wall. That something was LIDAR, light detection and ranging. Here is the part most people do not know. A modern autonomous vehicle LIDAR unit fires over 1.3 million laser pulses per second. Each pulse travels out, hits an object, and returns. Because the speed of light is a fixed constant, 299,792,458 meters per second, the system measures the round-trip time to calculate distance with centimeter-level precision. The result is not a photograph. It is a point cloud, a 3-dimensional map of every object within roughly 200 meters, updated 10 times per second. Picture a sonar map of the ocean floor, but built in real time around a moving vehicle in all directions simultaneously. The Waymo driver system uses 5 LiDAR units simultaneously, generating a point cloud with 1.4 billion data points per minute. Each point carries a position in 3D space and a reflectivity value. A stop sign, engineered to be retroreflective, lights up like a flare in that cloud. A child in dark clothing on a dark street still registers as a solid, 3-dimensional shape. That is why the sensor matters. But LiDAR alone has a problem that almost nobody talks about. LiDAR is extraordinary in clear conditions, but laser light scatters in heavy rain, fog, and snow. A heavy snowstorm can reduce effective LiDAR range from 200 meters to under 30 meters, less than 2 seconds of stopping distance at highway speed. This is why every serious autonomous vehicle system today uses at least 3 completely independent sensing modalities simultaneously. The second one is radar, radio detection, and ranging. Radar fires microwave pulses rather than laser pulses. Microwaves pass through precipitation. Rain does not scatter them the way it scatters light. A 77 GHz millimeter wave radar unit, the standard on production autonomous vehicles today, can track objects at up to 300 meters in a complete whiteout. It cannot produce a detailed 3D map, but it does something LiDAR cannot. It directly measures velocity. Through the Doppler effect, radar knows not just where something is, but how fast it is moving and in which direction, accurate to within 0.1 meters per second. A vehicle pulling out of a hidden driveway 250 meters ahead, invisible to the camera, degraded in the LIDAR, registers instantly in radar as a moving object on a collision course. The system begins braking before a human driver would have even registered a threat. The way these three systems, LIDAR, radar, and camera, actually combine is called sensor fusion, and the mechanism is more elegant than most engineering terms suggest. Think of it like a jury. Each sensor submits its testimony independently. The LIDAR says, there is a solid object 18.3 meters ahead, 1.2 meters tall. The radar says, that object is moving at 4 kilometers per hour, laterally, to the right. The camera says, that object is a person, wearing red, facing away. No single sensor is trusted completely. The fusion algorithm, running on a dedicated onboard computer with roughly 150 TOPS of processing power, cross-references all three testimonies in under 10 milliseconds. Disagreements are flagged and resolved by weighting the most reliable sensor for that specific condition. At night, LIDAR and radar dominate. In bright daylight at close range, the camera's semantic data, the ability to read a face, read a sign, read a brake light's color, takes precedence. The counterintuitive part is this. The system is more reliable precisely because each individual sensor is imperfect. Redundancy is not a backup plan. It is the design. The complications are real, and the industry does not talk about them loudly enough. First, LIDAR is expensive. A single Velodyne HDL 64E sensor costs $75,000 in 2016. Solid-state LIDAR units today cost under $500, but high-resolution scanning units still run between $5,000 and $15,000 each per vehicle. That price point makes full autonomy economically viable for robotaxis and freight, but it keeps it out of mass-market passenger cars for at least another decade. Second, sensor fusion fails in edge cases that engineers call corner cases, scenarios so unusual that training data barely covers them. In 2023, a Cruise Robotaxi in San Francisco dragged an injured pedestrian 20 feet after she was struck by another vehicle, because the fusion system classified her as a stationary road obstacle rather than a human. Cruise suspended operations shortly after. The sensors worked perfectly. The classification model was wrong. The hardware cannot solve a software problem. And crucially, the public's tolerance for autonomous vehicle errors is far less forgiving than its tolerance for identical errors made by human drivers. This technology is going to affect your life on a timeline most people are not tracking. If you work in trucking, the freight autonomy corridor between Dallas and El Paso is already running commercial loads with minimal human supervision in 2026. The American Trucking Association estimates 500,000 long-haul trucking jobs are directly exposed to automation by 2032. If you work in insurance, underwriting models that have been stable for 40 years are being rebuilt right now. If you drive in Phoenix, Austin, San Francisco, or Miami, there is already a non-zero chance the vehicle next to you at a stoplight has no driver. Watch for two things: the pace of federal rulemaking on autonomous vehicle safety standards, which stalled under previous administrations, and the price curve of solid-state LIDAR, which is the single biggest hardware barrier to mass deployment. 10 years from now, the car you drive today will look like a blindfolded vehicle by comparison. By 2035, industry analysts at McKinsey project that 12% of all new vehicles sold globally will have Level 4 autonomy, meaning no human required under specific conditions. What started as a graduate student's modified van at Carnegie Mellon has become a multi-sensor, real-time, three-dimensional model of physical reality